Hello viewers, in the previous lecture we studied number system and how a number in one number system can be converted to another. We also studied signed magnitude representation to represent numbers. Then we studied ones complement and twos complement representation to represent numbers. Apart from that, we also studied addition, subtraction and magnitude comparison of the numbers. At last, we studied the concept of overflow. Today, we are going to learn floating point representation and character encoding. A floating point number or real number can represent a very large or a very small value. It could also represent very large negative number and very small negative number as well as 0 as illustrated in the figure. As shown, a floating point number is typically expressed in the scientific notation with a fraction f and an exponent e of a certain radix r in the form of f into r raised to power e. Decimal numbers use radix r is equal to 10, while binary numbers use radix r is equal to 2. Representation of floating point numbers is not unique. For example, as shown, the number 55.66 can be represented as 5.566 into 10 raised to power 1, or it can be represented as 0.5566 into 10 raised to power 2, or it can also be represented as 0.05566 into 10 raised to power 3 and so on. The fractional part can be normalized. In the normalized form, there is only a single non-zero digit before the radix point. For example, decimal number 123.4567 can be normalized as 1.234567 into 10 raised to power 2. Similarly, a binary number 1010.1011 can be normalized as 1.0101011 into 2 raised to power 3. It is important to note that floating point numbers suffer from loss of precision when represented with a fixed number of bits, for example 32 bit or 64 bit. This is because there are infinite number of real numbers even within a small range of say 0.0 to 0.1. On the other hand, an n bit binary pattern can represent a finite 2 raised to power n distinct numbers. Hence, not all the real numbers can be represented. The nearest approximation will be used instead, resulting in loss of accuracy. It is also important to note that floating point number arithmetic is very much less efficient than integer arithmetic. It could be speed up with a so called dedicated floating point coprocessor. Hence, use integers if your application does not require floating point numbers. In computers, floating point numbers are represented in scientific notation of fraction f and exponent e with a radix of 2 in the form of f into 2 cross e as already discussed. Both e and f can be positive as well as negative. Modern computers adopt IEEE 754 standard for representing floating point numbers. There are two representation schemes under this standard. First one is 32-bit single precision scheme and the second one is 64-bit double precision representation scheme. Now let us discuss 32-bit single precision. In 32-bit single precision, floating point representation, as you can see, the most significant bit is the sign bit s, with 0 for negative numbers and 1 for positive numbers. The next 8 bits represent exponent e. The remaining 23 bits represents fraction f. So now we know how to represent 32-bit floating point number. So let us understand the normalized form now. Let us understand it with the help of an example. Now suppose that we have this 32-bit pattern. Here s is equal to 1, e is equal to 1, 0 0 0, 0 0 0 1 and f is equal to 0 1 1 and remaining bits as 0 which belongs to f. In the normalized form, the actual fraction is normalized with an implicit leading 1 in the form of 1 dot f as shown. In this example, the actual fraction is 1.011 remaining bits as 0, which is equal to 1 plus 1 into 2 raised to power minus 2 plus 1 into 2 raised to power minus 3, which is equal to 1.375. The sign bit s represents the sign of the number, with s is equal to 0 for positive and s is equal to 1 for a negative number. In this example, with s is equal to 1, this is a negative number. So we get minus 1.375. In normalized form, the actual exponent is e minus 127, so called excess 127 or bias 127. This is because we need to represent both positive and negative exponent. With an 8-bit e ranging from 0 to 255, the excess 127 scheme could provide actual exponent of minus 127 to 128. In this example, e minus 127 is equal to 129 minus 127 is equal to 2. Hence, the number represented is minus 1.375 into 2 raised to power 2, which is equal to minus 5.5. Then comes denormalized form. Normalized form has a serious problem. With an implicit leading 1 for the fraction, it cannot represent the number 0. Convince yourself on this. Denormalized form was devised to represent 0 and other numbers. For e is equal to 0, the numbers are in the denormalized form. An implicit leading 0 instead of 1 is used for the fraction, and the actual exponent is always minus 126. Hence, the number 0 can be represented with e is equal to 0 and f is equal to 0, because 0.0 into 2 raised to power minus 126 is equal to 0. We can also represent very small positive and negative numbers in denormalized form with e is equal to 0. For example, if s is equal to 1, e is equal to 0 and f is equal to 0 1 1 with remaining bits as 0, the actual fraction is 0.011, which is equal to 1 into 2 raised to power minus 2 plus 1 into 2 raised to power minus 3, which is equal to 0.375. Since s is equal to 1, it is a negative number. With e is equal to 0, the actual exponent is minus 126. Hence, the number is minus 0.375 into 2 raised to power minus 126, which is equal to minus 4.4 into 10 raised to power minus 39, which is an extremely small negative number, very close to 0. Now, let us do some more examples to understand the concept of normalized and denormalized form more clearly. Suppose that we have this 32-bit floating point representation pattern. Here, sign bit s is equal to 0, it means positive number, E is equal to 1 0 0 0 0 0 0 0, which is equal to 128 in normalized form. Fraction is 1.11 with an implicit leading 1, which is equal to 1 plus 1 into 2 raised to power minus 1 plus 1 into 2 raised to power minus 2, which is equal to 1.75. Thus, the number we get is 1.75 into 2 raised to power 128 minus 127, which is equal to 3.5. Let us try one more example. Suppose this is the 32-bit floating point representation pattern. Here sign bit s is equal to 1, it means negative number, e is equal to 0, 1 1 1, 1 1 1 0, which is equal to 126 in normalized form. Fraction is 1.1 with an implicit leading 1, which is equal to 1 plus 2 raised to power minus 1, which is equal to 1.5. The number is minus 1.5 into 2 raised to power 126 minus 127, which is equal to minus 0.75. One more example. Suppose this is the 32-bit floating point representation pattern. Here sign bit s is equal to 1, it means it is a negative number, e is equal to 0, it means it is a denormalized form. Therefore, fraction is 0.000, all the bits are 0 except the last bit, which is 1, with an implicit leading 0, which is as shown. With this, 32-bit single precision representation is over. We have done many examples to understand it. I hope it is clear to you now. Now, let us do 64-bit single precision representation. The representation scheme for 64-bit double precision is similar to the 32-bit single precision as shown in the figure. The most significant bit is the sign bit s with 0 for negative numbers and 1 for positive numbers. The following 11 bits represent exponent e, the remaining 52 bits represent fraction f. The value of a number n is calculated as, for normalized form, where e is greater than equal to 1, less than equal to 2046, n is equal to minus 1 raised to power s into 1 dot f into 2 raised to power e minus 1023. For denormalized form, where e is equal to 0, n is equal to minus 1 raised to power s into 0 point f into 2 raised to power minus 1022. We have a special case also, that is when e is equal to 2047, n represents special values such as plus minus infinity or NaN, not a number. With this, our 64-bit single precision is over. Now, let us summarize what we have learned so far. The sign bit s is self-explanatory, 0 for positive and 1 for negative numbers. For the exponent e, a so-called bias or excess is applied so as to represent both positive and negative exponent. The bias is set at half of the range. For single precision with an 8-bit exponent, the bias is 127 or excess 127. For double precision with an 11-bit exponent, the bias is 1023 or excess 1023. The fraction f, also called the mantissa, is composed of an implicit leading bit before the radix point and the fractional bits after the radix point. The leading bit for normalized numbers is 1, while the leading bit for denormalized numbers is 0. In normalized form, the radix point is placed after the first non-zero digit. For binary number, the leading bit is always 1 and need not be represented explicitly. This saves 1 bit of storage. In IEEE 754's normalized form, for single precision, E is greater than equal to 1 and less than equal to 254 with excess of 127. Hence, the actual exponent is from minus 126 to 127. Negative exponents are used to represent small numbers, very small, less than 1.0, while positive exponents are used to represent large numbers greater than 1.0, where n is equal to minus 1 raised to power s into 1 point f into 2 raised to power e minus 127. For double precision, e is greater than equal to 1, less than equal to 2046 with excess of 1023. The actual exponent is from minus 1022 to plus 1023 and n is equal to minus 1 raised to power s into 1 point f into 2 raised to power e minus 1023. Take note that n bit pattern has a finite number of combinations equal to 2 raised to power n, which could represent finite distinct numbers. It is not possible to represent the infinite numbers in the real axis. Even a small range, say 0.0 to 1.0, has infinite numbers. That is, not all floating point numbers can be accurately represented. Instead, the closest approximation is used, which leads to the loss of accuracy. If e is equal to 0 but the fraction is non-zero, then the value is in a denormalized form and a leading bit of 0 is assumed. Denormalized form can represent very small numbers close to 0 which cannot be represented in normalized form. Now, coming on to special values. What about 0? 0 cannot be represented in the normalized form and must be represented in denormalized form with e is equal to 0 and f is equal to 0. There are two representations for 0, plus 0 with s is equal to 0 and minus 0 with s is equal to 1. Then comes infinity. The value of infinity, for example 1 divided by 0, and minus infinity, for example minus 1 divided by 0, are represented with an exponent of all ones, that is, e is equal to 255 for single precision and e is equal to 2047 for double precision. Also, f is equal to 0 and s is equal to 0 for plus infinity and s is equal to 1 for minus infinity. Then we have another special case, that is called not a number value. Not a number denotes a value that cannot be represented as a real number, for example 0 divided by 0. Not a number, that is NaN, is represented with exponent of all ones, where e is equal to 255 for single precision and e is equal to 2047 for double precision and any non-zero fraction. With this, our floating point representation is over. Now, our next topic of discussion is character encoding, also called character representation. In computer memory, characters are encoded or represented using a chosen character encoding scheme. For example, in ASCII as well as in Latin 1, Unicode and many other character sets, code number 65 to 90 represents capital A to capital Z respectively. Code number 97 to 122 represent small a to small z respectively. Code numbers 48 to 57 represents 0 to 9 respectively. It is important to note that the representation scheme must be known before a binary pattern can be interpreted. For example, the 8-bit pattern 0, 1, 0, 0, 0, 0, 1, 0 could represent anything under the sun known only to the person who encoded it. The most commonly used character encoding schemes are 7-bit ASCII and 8-bit Latinx for Western European characters and Unicode for internationalization. A 7-bit encoding scheme such as ASCII can represent 128 characters and symbols. An 8-bit character encoding scheme such as Latinx can represent 256 characters and symbols, whereas a 16-bit encoding scheme such as Unicode can represent 65536 characters and symbols. Let us do them one by one, beginning with 7-bit ASCII code. It is a very well known fact that computers can manage internally only zeros and ones. This is true, and by means of sequences of zeros and ones, the computer can express any numerical value as its binary translation, which is a very simple mathematical operation. Nevertheless, there is no such evident way to represent letters and other non-numeric characters with zeros and ones. Therefore, in order to do that, computers use ASCII tables, which are tables or lists that contain all the letters in the Roman alphabet plus some additional characters. In these tables, each character is always represented by the same order number. For example, the ASCII code for the capital letter A is always represented by the order number 65, which is easily representable using zeros and ones in binary. 65 expressed as a binary number is 1000001. The standard ASCII table defines 128 character codes from 0 to 127, of which the first 32 are control codes, which are non-printable, and the remaining 96 character codes are representable characters. This is the ASCII table as shown in the figure. This panel is organized to be easily read in hexadecimal. Row numbers represent the first digit and the column numbers represent the second one. For example, the A character is located at the 4th row and the first column. For that, it would be represented in hexadecimal as 0x41. Because most systems nowadays work with 8-bit bytes, which can represent 256 different values in addition to the 128 standard ASCII codes, there are other 128 that are known as extended ASCII, which are platform and locale dependent. So, there is more than one extended ASCII character set. The two most used extended ASCII character sets are the one known as OEM, that comes from the default character set incorporated by default in the IBM PC, and the other is the NC, which is used by most recent operating systems. The first of them, the OEM character set, is the one used by the hardware of the immense majority of PC compatible machines and was also used under the old DOS system. It includes some foreign signs, some marked characters and pieces to represent panels. Then comes 8-bit Latin code. ISO 8859 is a collection of 8-bit character encoding standards for the Western languages. ISO or IEC 88591, a Latin alphabet number 1 or Latin 1 in short, is the most commonly used encoding scheme for Western European languages. It has 191 printable characters from the Latin script, which covers languages like English, German, Italian, Portuguese and Spanish. Latin 1 is backward compatible with the 7-bit US ASCII code, that is, the first 128 characters in Latin 1, that is code numbers 0 to 127, is the same as US ASCII. Code numbers 128 to 159 are not assigned. Code numbers 160 to 255 are as shown. Then comes the most used code called Unicode. Before Unicode, no single character encoding scheme could represent characters in all the languages. For example, Western European uses several encoding schemes in the ISO 8859X family. Even a single language like Chinese has a few encoding schemes like GB2312 or Big 5. Many encoding schemes are in conflict of each other, that is, the same code number is assigned to different characters. Unicode aims to provide a standard character encoding scheme, which is universal, efficient, uniform and unambiguous. Unicode standard is maintained by a non-profit organization called the Unicode Consortium. Unicode is an ISO standard 10646. Unicode is backward compatible with the 7-bit US ASCII and 8-bit Latin 1. That is, the first 128 characters are the same as US ASCII and the first 256 characters are the same as Latin 1. Unicode originally uses 16 bits called UCS2 or Unicode character set 2 byte, which can represent up to 65,536 characters. It has since been expanded to more than 16 bits, so currently it stands at 21 bits. The range of the legal codes in ISO or IEC 10646 is now to 21 bits or about 2 million characters, covering all current and ancient historical scripts. The original 16-bit range of 65,536 characters is known as Basic Multilingual Plain (BMP), covering all the major languages in use currently. The characters outside BMP are called supplementary characters, which are not frequently used. Now, Unicode has two encoding schemes, US2 called Universal Character Set 2. It uses 2 bytes, that is 16 bits, covering 65,536 characters in the BMP. BMP is sufficient for most of the applications. UCS2 is now obsolete. UCS4 called Universal Character Set 4 uses 4 bytes, that is 32 bits, covering BMP and the supplementary characters. So, with this, character representation is over. So, finally concluding, we have learned what is floating point representation. We did many examples to have a firm grip on the concepts of floating point representation. Besides, we have also learned what is character encoding and done various examples. I hope you understood the lecture. In the next lecture, we will start with a new topic. Till then, goodbye. Thank you.